Science in Action. Science in Action is produced by the West's oldest scientific institution, the California Academy of Sciences, now in its 100th year.
Thank you. May I pour you a cup of coffee? While I'm doing this, I'd like to mention a problem that has arisen. Now, I didn't plan to drink my coffee right now. What I had hoped to do was to drink it in a few minutes. So the question is, shall I add the cream now, or shall I add it later, say in about 5 minutes when I get ready to drink the coffee? Well, we can very easily make an experiment out of this by adding cream to one of them now, and then later, when we get ready to drink the coffee, we can test that against the other cup of coffee to which we will add cream at that time. Now, of course, there will be a certain amount of cooling in both of these cups of coffee, and that cooling will be due to the flow of heat. The flow of heat from the coffee to the cup and from the coffee to the air. Now, there will be a considerable amount of difference in the temperature of those 2 cups of coffee in 5 minutes. I have difficulty in remembering which one cools off the faster. But fortunately, we have as our guest on Science in Action a scientist who has the answers to all such problems. I'd like to have you meet him. He's an old friend of our program, Professor of Physics at the University of California, Dr. Harvey E. White. How are you there, Harvey?
Good evening, Earl.
Say, can you help us with this coffee problem?
I'm not sure about all the answers, Earl, but we'll try on this one.
Fine.
Here's a little diagram made up of 2 cups of coffee. This one hasn't had the cream added. It's black yet. This is the one to which cream has been added. Now, this cup here that's black started at the same temperature this one did, but being hotter, it cools off more rapidly. And we can show that with a little graph here. Suppose this represents the cup of coffee that's black. It cools off with time, so that in about 5 minutes, 4.5, 5 minutes, it's gone down almost to room temperature, but not quite.
This would be the time scale here in minutes, 1, 2, 3, 4, 5.
That's right. Now let's look at this cup. The first thing we did was add cream.
Yes.
Right away, that cooled it down from this temperature down to about there. Then it started cooling, but being now cooler than the other one was, it doesn't give out as much heat per minute, and it follows a curve that looks similar, but always stays below the other one. It goes along like this.
Oh, yes.
But now don't forget, we haven't added the cream to this one yet.
Oh, yes, the first one.
So now if we add the cream here at this point, it cools down below the other one and goes on.
Oh.
So now if you want your coffee to be hot at the end of 5 minutes, are you going to add the cream first or at the end of the time?
Well, the thing to do, quite obviously, from this graph is to put the cream in first, and at the end of 5 minutes, you'll have the hotter coffee than if you added the cream at the end of that period.
That's right. Just the opposite from what you might think.
Well, now, how does all this enter into the overall pattern of the transmission of heat?
Well, Earl, all of the various phenomena of heat transfer or heat traveling from one place to another can be classified under one of 3 classes of heat transfer, we call them. The first one is conduction, the second one is convection, and the third one is radiation. Now, conduction is a very, very slow process that takes place, as we'll see in our many experiments, over a period of time. It takes quite a while to conduct heat. Convection, however, is a more rapid process. But radiation is still more rapid, as we'll see later on.
Well, suppose we go back to that first one, conduction, and look at these various demonstrations that Bob Bell has set up here.
Well, here is a model, a crystal model, showing how the atoms would look in a solid. The reason for showing this is that I want you to keep in mind that all substances are made up of atoms and molecules. And it's the rapid state of vibration of the atoms and molecules that constitute heat. If you add heat to a solid, any solid, the atoms and molecules vibrate faster. If you allow it to cool off, the atoms and molecules slow down, so that heat or temperature is a measure of how fast they're vibrating.
Well, how would that affect this pan of water under which we have the heat?
Well, when you go to heat anything, Earl, you have to bring it into contact or nearby something that's hotter. And here in this pan of water, we bring it up, bring a hot flame up from burning gases or from a hot plate. And the molecules of that hot object hit the molecules of the bottom of the pan and set them vibrating faster. They in turn hit others, and this atomic motion is conducted through the metal to the other side where it heats the water up.
Now then, on our chart that we have here, we would have the flame at this point, and then we would have the flame transferring the heat to the bottom of the container, and then from that, by means of this same atomic motion, into the center where the water is.
That's right. It's passing on of the atomic motion from molecule to molecule.
Well, this next demonstration that you have here is one that is really quite interesting. Now, let's see. First of all, you have a heat container here, and you have a certain amount of steam that's passing over through here and down here, and then what are these various rods that you
Well,
have?
this is to show, Earl, that some metals, some substances are good conductors of heat and others are poor conductors of heat.
I see.
Here are 6 metal rods, all the same length, all the same diameter, but they're made of different metals. This first one here is copper, then aluminum, and here's brass and German silver, tin, and lead. Now they're painted with a paint that changes color when they get hot. Although they're all heated to the same temperature down here at the bottom, you see this one has changed color all the way up already. It's been going about 5 minutes, and it is a good conductor, copper. But look at this one over here, lead. You see it's changed color only this far up, showing that it's a poor conductor. So here we have different kinds of conductors, good conductors, poor conductors.
And all metals then will have this sort of a characteristic. In other words, it will either be poor or good as far as
Well,
conducting
some
is
in
concerned.
between. There are some semiconductors, we might call
Now,
them.
how about this cork experiment here? That is certainly a very ingenious
Well,
one.
this is another experiment in conduction, Earl. Here, I'm going to put a few drops of water in this little aluminum tube. This tube is mounted on the shaft of a motor. And I'm going to put a cork in the end of the tube now and stop it up good and tight. And now we'll put this wooden clamp around this shaft, and I'll turn the motor on. Now what will happen is the friction will develop heat. It will be conducted through to the tube, to the water, and cause it to boil. And then I hope steam will develop and blow the little cork out.
There she goes.
Here it was the conduction of the heat through the metal to the water that caused it to boil.
Well, that's really quite a weapon there, the way that cork popped out. Of course, all of us know about the advantages of metals that are conductors, such as copper and some of these others we've seen demonstrated. Copper in electricity, that is an electric field used for wiring and that sort of thing. But occasionally we have need of other metals that are non-conductors, such things used in insulating, glass, wool, lead shields for X-ray equipment, wood, and various other things. But how about paper now? What sort of conductor is that, Harvey?
Well, paper, Earl, is a very, very poor conductor of heat. But curiously enough, even though it's a poor conductor, if you make it thin enough and distribute the heat over a large enough area, you can conduct a lot of heat through a thing like a thin piece of paper. Now here's a very interesting little experiment with a piece of paper. This is ordinary typewriter paper, bond paper, folded into a little cup. Now what I'm going to do is pour a little water in this paper cup, and I hope it doesn't leak, and we'll put it over this open flame. Now don't be alarmed, Earl.
Now, let's see, there should be a scorch mark there. If anything's going to happen, I don't see anything at all.
Well, this paper can't possibly burn as long as that water's in there.
The water's starting to boil. Can we dump the water back in and see what the underside of that looks like?
Yes, let's try that. See, the paper's not scorched at all.
Not a thing there. Well, now, suppose that you had a thicker piece of material in the bottom of this. Would that make any difference? In other words, the heat would have to travel further through the material.
I anticipated this, Earl, and so I have another little box with a piece of cardboard in the bottom of it, see?
Well, that has cardboard in there that you put on top of the paper.
That's right. It's about 10 times as thick as that paper. Now let's see if that helps us any. Put a little water in it and put it on over the open flame. Are you hoping it'll burn, Earl?
I'm just looking down here to see what... Well, I see a scorch mark appearing there. It's
Well, let's
certainly
pour the
burning
water
out.
There's a scorch?
There's a scorch mark already. In other words, then the thinner the paper is, the more difficult it is for it to burn because the heat will be transferred through.
Yeah.
And yet the heavier paper here, the heat wasn't able to go through as readily.
That's right. Let's put this back on here and let it go a while. See if we can get the water to boil.
In other words, we come back to that later in the program. We'll find that the water's still boiling and the paper will not
I
be
think that's
touched.
a good idea.
Fine. Well, now this rod that you have here is another quite interesting one. Let's see. First of all, a piece of metal here. This is copper.
Copper.
And then hardwood here. And the next thing is what? A piece of paper around there.
Piece of paper again. Copper, remember, is a good conductor. The wood is a poor conductor. Now I'll put the paper around it, too, and hold it tight against them and try to burn the paper.
Oh yes, we have a scorch mark there. Let's take the paper up, and we see what happens. The scorch mark corresponds with the wooden area, but there's no burn mark on the copper part. Now that
That's
again
right.
is conduction.
That's right. The heat flowing through the paper hits the copper, flows quickly into the inside of the copper because it's a good conductor. But here where it strikes the wood, the heat flows through the paper, hits the wood, and stops. It can't conduct it away fast enough. Paper gets hot and it burns. So here's a good conductor, poor conductor, with a piece of paper around it.
This water, we've all seen how water can be heated. It's a poor conductor, and yet it quite often heats quickly over an open and hot fire. We see it happen, but just how does it happen and why does it happen?
Well, of course, water is actually a poor conductor of heat, and yet the pan of water will heat quite quickly due to the second method of heat transfer called convection. Now, convection current is an actual flow of hot water from one place to another. Here we come back to our diagram of the pan, you see, Earl. When the heat is conducted through the bottom of the pan, it heats up the water here in this area, and the hot water has expanded. And it, being lighter now, rises to the top. It goes up here toward the top of the pan. Well, if warm air water rises, cold water from the side has to come in and take its place like that. And again, cold water here comes down the sides to take its place, and in turn, cold water comes across the top. Now, you see what happens here? We have a current.
Oh, current is set up there.
A convection of current, of water, from the hot region here around continuously, and that's why a pan will heat up quickly.
Well, this is the same sort of thing that we have in lakes various times of the year, and also happens in the ocean, these convection currents.
Yes, the warm water rises and gives us these ocean currents.
Well, now, what would be some practical application of these various convection currents?
Well, in this experiment, Earl, we're going to set up a convection current of water around this glass tube in the shape of the letter O. This is filled with water, and we're going to heat one corner here with a flame.
Yeah, we can move this right over there.
Burner.
There it comes.
And then to show that the water is going to flow, you see it's being warmed here, and being warmer it expands and rises.
Yes.
It'll go up the side of the tube and across over and down, and we'll get a convection current clockwise around this letter.
And this dye that you have then would indicate that.
That's right. In order for you to see that the water is moving, I'll put this dye in the top. See, there's quite a convection current there already set up.
Certainly going around there.
You see that all right?
In other words, a poor conductor such as water can be rapidly heated due to this convection current which is set up.
Yes. Now, there are practical values to which this can be put, Earl. Many houses and buildings are heated by a convection water current. They're in the basement of the building. There may be a furnace that heats a tank of water. The water rises through a pipe and flows through the various rooms of the house and back again where it's heated again. We have a convection current of hot water.
Well, incidentally, the radiators, of course, are the just extensions of the pipes. What they do is to give a larger heating surface so that the house or the room will heat up much more quickly.
That's right. And, of course, we have another kind of convection current in the house, too. Around that radiator, there's air. And this air is warmed, and as it warms, it expands and it rises. And then the cold air comes in along the floor, and we get the same kind of a convection current we had here, only in this case it's the air going around the room. So two convection currents are involved in such as this heating system.
Yes, well, it's certainly obvious that the hot air heating system is very similar to the hot water heating system. In other words, these systems in houses, generally down in the basement, there is a furnace, or sometimes the furnace will be on the main floor, but always there is a duct that comes from that furnace, and it goes in usually at the floor line, somewhere around the baseboard. And then from there, the hot air comes in, and it rises up one side of the room, travels across the ceiling, and down the other side, across the floor, to return to the furnace by another opening in the floor or the baseboard.
Now, here's another experiment in convection, Earl. Will you hold that glass cylinder?
I certainly will.
I'm going to light a candle here at the bottom of this box, and then I want you to place the glass tube over the top of it and press it down on that cork so that no air can get in at the bottom. Of course, it's still open at the top. And the candle is burning up oxygen in here, and the warm nitrogen that's left rises up the tube.
Now, there it goes out.
Well, yes, of course, because the oxygen was soon used up, you see, and it needed oxygen to keep burning. Now we'll do the experiment again, Earl, and when you put that in there, put that tube over there, I'm going to put in a little piece of cardboard down in here.